Thank you. All right, thank you all for coming, and those of you watching online, thank you for watching. Those of you here, if you like it so much you want to watch it again, give it a thumbs up. That would be awesome. So as I said, I'm Scott. I'm the lead maintainer of CircuitPython for Adafruit. Today, hold on. It was running away from me. Okay, so I go by Tan Newt online. As I said, I'm Scott. I'm a freelance software engineer, but I work full-time for Adafruit. They're my only client. This is Blinka, the snake. It's our mascot. Really fun to have a snake puppet. It's quite unwieldy. Anyway, here's our plan today. I'd like to up the ante. I've given this talk before, but I've never done it with 2 demos on a laptop that is not mine, so sit tight. We'll see how that goes. So what we're going to do is we're going to start with just a circuit, not playground, but CircuitPython demo. You have those badges that were in your goodie bags, and I just want to give you a brief taste, if you haven't had a chance to play with it, what CircuitPython is. And then what we're going to do is we're going to talk at the very highest level of CircuitPython, and then go down and talk about all the layers underneath it until we get down to the bottom of the hardware. And then we'll wrap up with a Gameboy Demo, which is the, you can make even existing hardware great with CircuitPython. Okay, so not a circuit playground because I decided to use the badge. But let's do this. So what I have here is just the stock edge badge that we all received in our goodie bags. There's 5 NeoPixels at the bottom, and I'm going to make those turn on, and I'm going to show you how easy it is to do that. So first, I have just a micro USB cable that I'm going to plug in here. And again, this is not my computer, so let's see. All right. It pops up as this keyboard thing because it hasn't seen the device before. So you can just X out of that. Let's escape. And what it does is it shows up as a USB device. So we have this CircuitPy drive that has showed up because I plugged it in. If we open it up, we see a code.py file. Now this is the scary part. I've not installed any text editor at all. So we're going to actually use text edit that comes on a Mac by default. I did try this earlier. I think it works. And I know how to make the font bigger. But it thinks I'm writing human text, so it's like, I don't know what this stuff is. So this is almost the exact same code that's shipped on the badge by default. We have some imports, and we have this nice library called PyBadger that makes everything available that's on the badge. The 2 things that I've added here are accessing the pixels on the bottom. And I've set the brightness to 0. That's why they don't show up at all. But hopefully we have sunglasses in the front row. It might be a little bright. But if I change it to 1 and then I hit Command S, it should change. I can't actually see it. Did it work? Awesome. So the point is that CircuitPython is really easy to get going with. I didn't install anything on this laptop. As I said, it's not mine. But it's a text file with a USB drive, something that most people have had experience with, and they understand it and are comfortable with. So that's what I mean when I say supercharge. I mean supercharge by making it easy to access your hardware. So I'll show one more thing, to push my luck. It should be purple right now, and let's just make it straight red. So all I'm doing up here is I'm saving. So I could actually go File Save, and it's unhappy for some reason. I think this is a text edit specific thing because I use a Mac and I use Atom, and it works just fine. So text editors can make it better. So let's move on. I don't know why it does that. But always eject your drive if you want to be friendly to it. Otherwise, it can come back to bite you. Okay. I don't want to run down my battery. like full brightness neopixels on 2 colors will definitely run down your battery. Okay, so let's jump back into our slides, not from TextEdit. That's full screen. That's our plan, that's our demo. Okay, so at the highest level, what is CircuitPython? And we think of it 2 core things. We think of it as code, and we also think of it as community. It's a very important distinction, especially as a project lead, to recognize that there is time and effort spent into making a good community. And we'll talk just a little bit about what that means. But first, let's talk about code. Hopefully, as I demonstrated, Python is the easiest way to iterate on software. And we've brought that to microcontrollers with CircuitPython. The code and the tool chain itself travels with you. So if I handed John Park the code up here in the front, he would be able to edit the code that I had and start where I left off, which is, I think, really awesome. If you're interested in seeing the low-level details, this is the GitHub link for it. And I want to give credit where credit is due. MicroPython there's a very strange sound happening in this room, and it is now done, for those of you who can't hear it. So we were built on MicroPython. They did the work to bring the goodness of Python to microcontrollers, so credit where credit is due there. On the community side, we have a code of conduct, which lays out what we expect, how we expect people to behave, and we are willing to enforce it, which means that we have a very nice and friendly community around us, which is always awesome. That community lives both on our GitHub and our Discord server, and I'll have a link to the Discord at the end. Right now, we have 190 CircuitPython compatible libraries, which is growing and growing and growing. So this is all the different devices that we could support. And we have 83 plus supported boards. So this is what our download page looks like. Because we have 83 supported boards, we want to try and get you to the newest version of CircuitPython the fastest we can. So if you go to circuitpython.org/downloads, we'll show you all the different boards that we run on. These are all Adafruit boards, but we are very, very interested in adding support for boards that are not manufactured by Adafruit. There are a number that are available. They're just not on the slide. So if you have a board, reach out to me. I would love for CircuitPython to run on it. But these are not also manufactured by Adafruit, and they are also not manufactured anytime recently. So for those of you who don't know, these are all versions of the Nintendo Game Boy. The one on the furthest left is the original Game Boy. Has the model number DMG for dot matrix grid, and they're chunky. I have a green one here that I will use later. No more spoilers than that. But it is the original. The one in the middle is the Pocket, where they really cost optimized and shrunk down the same size and same functionality. And then on the right-hand side, we have Game Boy Color, which took basically the guts of the Game Boy and just added one last step to add color palettes at the very end so that you could get colors out. This is what they look on the inside. The general gist of how these work is that the kind of top chip in the middle, it actually is labeled CPU, and that's basically where all the logic lives. So the CPU, the sound generation hardware, the pixel generation hardware is all within that one chip. And then the code actually lives on a cartridge, and the cartridge is accessed through the big plastic bit there. It has a bunch of contacts on it that read the memory that is stored in the cart and executes it on the CPU. So this is what carts look like. On the left-hand side is the Tetris cart. It's kind of as basic as you get. It's just a piece of memory that it can load code, and it could load the bitmaps that it needs and the sound information that it needs to run Tetris. It doesn't have any save state, so you always start at the very beginning of Tetris, and because it's very simple. There are actually some games where you would learn a cheat word so that you could skip to where you were later. But they also came up with a way to do save states, and this middle cart, Mary Kate and Ashley's Pocket Planner, is an example of that. It's cut because I go to the store and I buy cheap Game Boy cartridges just for the plastics. And I'll talk about that just a little bit later. But a couple things I want to point out. There's definitely more than one chip on this cartridge, and the circular thing in the top right is actually a battery. So this is before we had technologies that could store bits without battery power. So no SD cards, no flash technology. Instead, what they would do is they would just put a battery in RAM. So it's all RAM, but it's battery backed, and it saves your stuff. So if you've been keeping your Game Boy from when you were little or when you had it, and you have like Pokemon that you collected when you were like 10 maybe, make sure you replace the Game Boy cart and back it up before the battery dies. Hopefully it hasn't already, but just a general warning. And you'll see if you ever go to like retro game stores, they'll say like new save battery, because they usually do that for you. And it also has, again, the regular memory that stores all of the assets and code for the game itself. Now on the right-hand side is a cartridge that I designed. You can see it's Osh Park purple. And this is a little bit different than the other two. So let me go into that. Here's a bigger view. And it's not, well, it has memory, but it's also a microcontroller in and of itself. This idea of using a microcontroller to mimic the memory of a cartridge is not new. There's a video online of somebody who actually used an STM32F4 as a Game Boy cart previously. And the general idea of how this works is the Game Boy is saying, hey, give me an instruction or give me data, and it does that at a 1 megahertz rate. So whatever you put on the other side has to be able to keep up, to keep the Game Boy CPU thinking that everything on that side is very dumb. And so that's the challenge. I chose to use a SAMD51, which is 120 megahertz, and it also supports CircuitPython. So if you didn't realize it before, well, we said it earlier, I love putting CircuitPython in things because it makes it really easy to program. And the way that I thought I could make programming Game Boys easy is by making the cart smart and then just kind of telling the Game Boy, oh, dude, just do this. Oh, just do that. Play the sound, as we'll see in just a bit. But let's talk about how that works and convince you that CircuitPython is quite awesome. So there's a number of layers. We're software people. We like abstractions. So let's just talk a little bit from the top to the bottom what those layers are. At the very top, we have Python code. This is pure Python code that we could use to make it easier to access different parts of the hardware. So in our badge example, or in our badge demo, that was the PyBadger class. So that's pure Python that's meant to make things easier. Below that, we have a Python API, but that Python API is actually implemented in C. So that's kind of like your dependency-free level of Python. Then you have this intermediate C level that's just taking all these Python objects and converting them into C objects. So you take a byte array in Python and make a C array out of it and get the length and store the length separately because it's C. And then at the very bottom of that, below that, you have what you would normally see if you were doing embedded development, which is C level, probably register accesses that can do time-critical things and be specific to the chip that it's implemented on. And then we'll talk a little bit about what the wire the data on the wire to the Game Boy actually looks like. So the demo that we're going to try to do is we're going to try to play a sound triggered by Python on the Game Boy. And then depending on how this cooperates, we may try to make it sound really cool too. So the way that we play a sound is there's an 8-bit register at this magic address that causes a sound to be played. It's the bit 7 there. And so how do we get from Python? So this is our Python example code where we're just doing a, hey, at this offset in the memory, store this value. Right? So from Python, we're able to do that. How do we get all the way to the bottom? We talked about the layers. So this is kind of, this index access is how we trigger that kind of whole chain that we just talked about. And I'm not going to go into all those details, so fewer slides of code. So some layers later, we get to the bottom. And so this is our C code. It is also a bit truncated, but the general idea is that we are accessing direct C structs that are defined by the atmel samd, and we're using it to do DMA. So the way that we keep up with the rate of the Game Boy saying, hey, every whatever period 1 megahertz is, give me a byte and so that I can run it and execute it, is that we use DMA. And that DMA, Charles was talking about lookup tables. Well, the SAMD has like 4. They're very small, they're very simple lookup tables, but what you can do, the DMA, or the Game Boy cartridge has a clock line, a read line to tell you whether the CPU is reading or writing to the cartridge. And also, we want to pay attention to A15, which is the upper bit of the address, because if it's 1, then that means that other things in the Game Boy are being written to, not the cartridge. So we use the SAMD51's CC LUT to generate a signal out of those 3 inputs. And then that signal is used to do 2 things. 1, it clocks the DMA. So we're moving a byte from RAM into the thing that sets the pin out, right? So your GPIO peripheral. And then the other thing is we also have a tri-state bus that we can tell it, oh, like leave the data bus as is, or give it the byte that we're doing. So we use this signal to set that. So what does it look on the wire? So here we have clock at the top, we have address in the middle, and then we have a data line. And when it's in the middle is when nothing is happening on data. Something else can be setting the data of it. That's high Z, as you may know. And so the first thing we do is we get an address in. We actually don't read it. We don't actually know what address it's reading almost always. There's one case that if you're curious, you can ask me later. But the Game Boy actually doesn't care, right? It just wants the byte. And it's used to it being actually the same, but there's no caching or anything. So you can just give it whatever you want, and it's just fine. So the first thing we give it is the instruction to load a value into the register A. The 0E is the instruction. That's why I made it yellow. So this is our value. That was the 0B blah, blah, blah in Python. Here's the 3E, which is giving us the last byte of the address. And then there's a special instruction that takes C and adds it to the base FF00. It's a convenience function. I don't think the original Z80 processors had it, but the Game Boy CPU is a little weird. And it's convenient because basically all of the special registers are within that range. So it makes it a little bit quicker to access them all. So with that, we've successfully written a bit from Python all the way down to C into the Game Boy register. And it continues on. Now let's do a Game Boy demo. And we have some time, so hopefully we can make some really funky sounds. And maybe we'll have to restart it, we'll see. So if we get this turned up, we should hear Adafruits dropping down. Nothing? Ooh. Oh, sorry. Maybe I should not hold it when we do that. It won't play again. Let me restart it. No? Didn't work. It's so touchy. Okay, let's go to the backup. Can you turn it off and I'll unplug it? I'll just do it with the mic. Okay, so here we go. There we go. That's the sound I wanted to hear. Okay, so let's see what we can do with this. So just like I did in the first demo, I'm going to just take the micro USB, and the Game Boy cart has a micro USB on it. So I'm going to plug it in, and you'll hear it actually, it will restart after it accesses it. Maybe. Well, we got CircuitPy, which is good. trying to see it. So every time a file is written to the CircuitPython drive, even if it's because like I opened it up and Mac is like, oh, let me write something, it will restart, which can be fun and cannot be fun as well. And I actually have a bug right now that I'm trying to work around. So the reason you get that classic chime at the beginning is because I might actually get out of sync with the Game Boy, and the Game Boy will run off and do what I don't want. So I actually have it right now. The Game Boy cartridge can reset the Game Boy. So I'm doing that right now every reload just to make sure I start from the same place that I think I am. OK, so we've got our text edit window. So if you notice, I'm like sharing the mic with a Game Boy. Like, anybody want to take a picture? I love Game Boys. Thank you for bearing with me. OK, so I've got the code up here. This is basically what I had on the slide, except I've exposed or I've commented out every register that is involved in generating a sound on the Game Boy. And I have notes on here of what each individual bit does on those sound registers so that I can stand here and hopefully play with them. Now we had the trouble where it was like not happy writing it later, so I'm just gonna jump to the best part, just in case it doesn't work. Did you notice that there was actually a third tone being played? So it's like bum bang, and it's trying to play the same note at the same time now. But the best register in this register set is the sweep register. And what this does is it changes the frequency over the duration of the tone. And it's typically used for all of the sound effects that you've heard in many, many Game Boy games. So we're just going to jump straight to the end and play that. So let's do a save. So all I did here was I uncommented it. And hopefully we'll have some time to actually play with those bits. But let me just try it. And here it goes. It's very short. Let's see if we can make it a little bit longer. I think that it's resetting again. It's very fast to edit because it likes to do that. Oh, you know what? It might be trying to do it on my behalf. Let's just uncomment stuff and see what it does. It's restarting again. It's all the same. OK, here's what we might have to do. Because text edit, I think, is confused. Actually, maybe if we just quit. Discard. Open again. Does VI come by default? OK, hold on. I can't hold the Game Boy and type at the same time. I have applications down there. You want to hold it for me? Sorry? Command space. Thank you. Oh no, it's not Colmac. Let me look at my fingers like I'm a rookie. Yes. So it's just a drive. Works like a normal drive. Oh, Catalina. Or not. Sudo. It's not my laptop. Let's try it. Maybe it requires a password. I don't know. OK, hold on. Aw, good job, Hackaday. Sorry? Nano.
Permission.
Let me eject and reset the Game Boy. It might be that side. And I'm 4 minutes left. I do have wrap-up slides, too. At least we got something out of it, right? Oh, okay.
I have heard it in person. It was amazing.
All right, we loaded the file, and we wanted to make it longer. I think it's this that's making it short. Didn't get it. Wait.
Make it shorter.
Did I make the volume 0? Volume is here. All right, let me comment that back out. There's also duration here. Here's time. Let's see what this does. Last one, then I'm done. It's like really slow to flush. Here it goes. Oh, I broke it. Okay, sorry. That'll do. Thank you for all for helping me. Thanks, John. If you want to come play with it, I'm happy to let folks poke around at it. But let's finish this. All right. I just have wrap-up slides, and then we're good. So if you want to know more about how the Game Boy works, this talk actually got me into it. It will cover both how the sound hardware works and how the pixel pipeline and all that stuff works. Covers all the registers. It's super cool. I highly, highly, highly recommend it. And so what are the takeaways from this talk? First, CircuitPython is the easiest way to program hardware. I hope I demonstrated that, even though I couldn't twiddle the right bits. For those of you who've done C, remember you can always fall back to adding stuff to C if it needs to be faster or you need access to something you don't have access to. And that existing hardware can benefit from CircuitPython. So if you've designed something already, we'd love to add CircuitPython to it. How do you do that? We support the SAMD21, 51, NRF52840, and the STM32F4 series of microcontrollers. If you have something that you've designed with any one of those things, reach out to us. We'd love to get CircuitPython running on it. We're also planning on doing the IMX RT series, which if you haven't looked at, you should. They're very inexpensive, and they're like 500 megahertz at minimum. With USB high speed, including the PHY. So I highly recommend taking a look at those. The Teensy 4 has it currently, so if you want to play around with one now, check out the Teensy 4. This is our link to our Discord. We'd love to have you pop up and ask questions. If you're having trouble with your badge, we'd love to answer any questions you have there. Again, here's a link to the GitHub. Everybody get a picture of it? A couple more. I also do post my slides on my GitHub account, so you can go to github.com/tannewt/presentations, and all the presentations I do go there. And this is my contact info. I go by Tannewt on GitHub, on Twitter, so you can reach out to me there. There's my work email, so you can drop me a line if you need a pointer to where you want to look at. Otherwise, you can go to circuitpython.org to get more information. So thank you very much for all attending, and for those of who are watching it later, thank you as well.